Good morning, students. So far we have seen about internal combustion engines. So that is about Otto cycle, diesel cycle and dual cycle, and the problems which are related to that is objective type and numerical type problem related to those. So now in our third class, that is in this class we are going to see about power engineering. So that is about Rankine cycle. Okay, so in Rankine cycle we are going to see the basic introduction about Rankine cycle, and then some problems related to this Rankine cycle, and then about regeneration and reheating, and then the problems that is both objective type as well as the numerical type questions. So we can see all those in this class. This is our third lecture, so that is about Rankine cycle. So Rankine cycle we are going to see about the basic introduction about the steam tables, and then simple Rankine cycle, then the concepts of regeneration and the concept of reheating. So when you go for the introduction about this, what is that Rankine cycle? So it comes under this power engineering. So power engineering, it deals with the study of energy and its sources and the utilization of the energy for power generation. So the power is generated by prime movers. So example, hydraulic turbines, steam turbines and diesel engines. So large amount of power is generated using these prime movers. So in a site or a layout called as power plants. So all the equipments, machineries which are required for this power generation is located at the respective places. Then energy may be defined as the capacity to do work. So the energy, it exists in various forms. So such as mechanical energy, thermal energy, electrical, solar and so on. So electricity is the only form of energy which is easy to produce and transport and easy to use and also easy to control. So the electricity consumption per capita, which indicates the index of the living standard people of a particular place or a country. Okay, so the utilization of energy is the indication of the growth of the country. Okay, so generally, so these energy resources, they are classified so into conventional and non-conventional. So conventional is otherwise called non-renewable and non-conventional is renewable. So these are some of the examples for this non-renewable energy and renewable energy. So how will you classify the power plants? So this is classified that is according to depending on the type of energy source, the power plants are classified, and these are the general classifications of these power plants, and various vapor cycles and combined power cycles. So the term vapor cycle implies the working fluid is alternatively vaporized and condensed during the cycle. So on the gaseous phase, typically it exists near the saturated vapor line. So in this case, so the working fluid, so that is the working fluid may be steam or water, so it is alternatively vaporized and condensed during the cycle. So this working fluid, so it is used in vapor power cycles, which is cheap, which is readily available, non-toxic and has higher enthalpy of vaporization. So most vapor power plants are steam power plants. So it is powered by coal, natural gas or otherwise nuclear power. So a Carnot idealized vapor cycle, so it operates under the saturation conditions. So that is it is the representative versions. So they are given in the diagrams. We all know about this Carnot cycle. So the maximum efficiency is obtained in the Carnot cycle. So that is 1 minus TL by TH. TL indicates the lower temperature and TH is the higher temperature. So this Carnot cycle is an impractical cycle. It is an impractical as a model vapor cycle, and it cannot be achieved in actual devices. So when you go for this power engineering, so we have to know about this steam, that is steam tables, steam formation, that is Mollier chart, what are the properties that we can measure with the help of Mollier chart. So everything should be known to you. So the steam formation, so this is the diagram which represents the formation of steam. So initially solid phase, so when it is heated, when positive amount of heat energy is given to you, then it is converted into liquid phase, and then on further heat addition, that is converted into gaseous phase. On the removal of the heat, so it is the gaseous phase is converted into liquid phase and then solid phase. So this is the diagram which represents the formation of steam. and Mollier chart. You can see the Mollier chart. So where we are going to draw the graph between the enthalpy and entropy. So enthalpy is given in terms of kilojoule per kilogram, and entropy is given in terms of kilojoule per kilogram Kelvin. So when you go for the steam tables, so you have it consists of two sets of tables. So that is, one is about saturated steam tables and other one is superheated. So in saturated you have temperature and pressure. So you can measure the properties of that is dry steam, wet steam and superheated steam with the help of these steam tables. Okay, so the steam tables, the following notation is used in steam table for temperature, pressure, specific volume, internal energy and all. So this is a simple representation of this steam table. Then what are the important points that we have to measure? So that is in steam tables it gives all the values for 1 kg of water and 1 kg of steam. In the steam table it gives the values of properties from the triple point of the water to the critical point of the steam. Suppose if pressure is known, and so you can go for the pressure table, and temperature is known, you can go for the temperature table. So at low pressure the volume of saturated liquid is very small as compared to the volume of dry steam, and usually the specific volume of the liquid is neglected. So this is the condition why the specific volume is neglected. And some definitions are there about subcooled or compressed liquid, then saturated liquid, wet steam, dry steam, then saturated steam and superheated steam. So then about the quality. So when you go for the subcooled liquid, it is a fluid under thermodynamic condition that it forces it to be a liquid. So saturated liquid, it is fully in the liquid state, but it is about to vaporize. So the liquid which is about to vaporize is saturated liquid. And wet steam. So when the wet steam contains water in the form of finer water particles, so that means water particles are suspended in the steam. And dry steam, so it contains no moisture. So the value of X, that is equal to 1. In case of saturated steam, it is the steam at equilibrium with the liquid water. So when you go for superheated steam, it is the steam which is heated above its boiling point. Okay, so above its boiling point, that is saturation point. And when you go for the quality, it is nothing but the quantity of dry steam in 1 kilogram of wet steam. So steam formation, how the steam formation occurs, so you can see here, so sensible heat, latent heat and the saturated condition and then superheated state. So the superheated conditions. So this, you should know about the formula of dry steam, wet steam and superheated steam. So all the formulas should be known to you for entropy, for enthalpy and entropy, and also what is the specific volume for each and every conditions. So you should know the formula, so that is about internal energy, specific enthalpy and specific entropy for wet steam, dry steam, saturated. Dry steam is nothing but saturated, and then superheated steam. So you should know the formula. So you have to be thorough with the formula, and you should know when you have to use these formulas. Okay, so it depends upon the condition. When you look at the problems that are given in the gate questions, so you can easily say, so what is the condition that prevails? So based on that, you have to select the respective formulas. So for that, you should know, so when, what is the condition of dry steam? That is, when X is equal to 1, it becomes a dry steam. When it is, when the value of dryness fraction increases, that is, but it not reaches 1, so that means it contains moisture content in it, so that means it is a wet steam. Okay, so Rankine cycle. Now we are moving to the Rankine cycle. So it is the fundamental operating cycle of all power plants where an operating fluid is continuously evaporated and condensed. You can see here. So the low pressure vapor condensate, so from this condenser is sent to the steam generator or boiler. So with the help of a feed pump, this feed pump it compresses that liquid. So that is condensate from the condenser and sent to the steam generator. You can see here the temperature entropy diagram. So you can see the low pressure condensate, not refrigerant, the low pressure condensate from this condenser. So it comes from the condenser and it is pumped with the help of a feed pump. It is pumped with the help of a feed pump and then it is sent to the steam generator. That is, this condition it refers to boilers. Then it is expanded. Then the steam is expanded in the turbine. So the expansion takes place isentropically. The expansion takes place here, it is isent. So the entropy at that is 3 to 4, it remains constant. So the amount of heat energy that is added in the generator is Q1, and in the condenser, that is the amount of heat energy that is extracted is Q2. Okay. So this is the working function, that is what happens in 1 to 2, what happens in 2 to 3, and what happens in 3 to 4 and 4 to 1. So when you go, as I said earlier, the pressure of the condensate is raised in the feed pump because of the low specific volume of liquids. The pump work is relatively small, and often the pump work is neglected for these thermodynamic calculations. When you go for isoboric heat transfer, that is 2 to 3 is isoboric, that is a constant pressure. So heat transfer takes place, that is high pressure liquid enters the boiler from the feed pump, that is 1 to 2, and is heated to the saturation temperature. So further addition of energy causes the evaporation of the liquid until it is fully converted into a saturated steam. So in case of 3 to 4, so the vapor is expanded in the turbine, which produces some work. That is, so the conversion of some form of work is takes place into other form, and thereby the electricity produces. So in practice, the expansion is limited by the temperature of the cooling medium and by the erosion of the turbine blades by liquid entrainment in the vapor stream as the process moves further into two-phase region. So the exit vapor quality should be greater than 90%. And when you go for the 4 to 1, that is isoboric heat rejection. So the vapor liquid mixture leaving the turbine is condensed at low pressure, usually in a surface condenser. So using the cooling water. Okay. So the formulas which are related to this simple Rankine cycle is the work done on the pump is given as WP is equal to H2 minus H1, and the energy added in the steam generator is given as H3 minus H2. Then work delivered is that is by the turbine is H3 minus H4. The energy rejected in the condenser is Q2 is H4 minus H1. So the thermal efficiency eta. So the same formula you are going to apply. So eta is equal to, so that is output by input. So the output is nothing but the work done. Output is the work done, and the input is the amount of heat energy that is supplied. So work done is work done by the turbine minus work done by the pump divided by the amount of heat energy that is supplied. So Q1 minus Q2. So what is Q1 minus Q2? So that is the amount of heat energy. Here it is the amount of heat energy that is added. That is Q1 is the amount of heat energy that is added, and the amount of heat energy that is rejected. So Q1 minus Q2 is the work done. So H3 minus H2 minus this is H4 minus H1 divided by amount of heat energy that is added is H3 minus H2. So you can write as H3 minus H4 minus H2 minus H1 divided by H3 minus H2. So this H3 minus H4 is nothing but the work done by the turbine, and work done by H2 minus H1 is the pump divided by the work done by, that is H3 minus H2 is the amount of heat energy that is supplied. Okay, so this is the formula for efficiency in case of simple Rankine cycle. So you have to use this formula. Okay, so you have to use this formula so for the problems that are given to solve this Rankine cycle, because in gate question you can see that you are getting mostly you are getting the Rankine cycle so with regeneration and reheating. So you have to concentrate. So only when you know the principle of Rankine cycle, so you can go for the further addition of regeneration and reheating. So it carries this Rankine cycle itself carries around 3 to 4 marks. So you have to be thorough with this Rankine cycle so that you can easily get this mark which is given in this. What is that? You can easily work out the problem which is given in this Rankine cycle, and you can get that marks. Okay. So the next is a problem is given like this. So you will get only these kind of problems in your gate question. Okay, so you can see here in a thermal power plant operating on a Rankine cycle, steam having enthalpy H is given to you, then entropy is given to you, which is produced at 3 megapascal and 300 degrees centigrade, and it is fed to a turbine where it expands to a condenser pressure of 5 kilopascal. Then the value of the enthalpy at fluid condition and at gaseous condition are given to you, and the entropy is also given for this fluid, and this gaseous condition is given to you. What is the work output of the turbine? So you have to neglect the pump work. So what is the net work output? So the net work output, you can see that it is H1 minus. So it is H1 minus. This is the diagram which which represents the Rankine cycle. So you can see that, so 1 to 2. So expansion at turbine. So the expansion is isentropic expansion. The expansion is isentropic expansion. So when you look at this diagram, you can say that S1 is equal to S2. Okay, so this is the hint for you. So only with the help of this, you can find the value of this work output, that is H1 is given to you, H2. You have to find the value of H2. So you have to find the value of this H2. So okay, right. So if you find the value of H2, so that is the work output, that is equal to H1 minus H2. So how will you find this? The only hint is we know that the expansion takes place at isentropic process. So the value of H1 is given to you, S1 is also given there, and we know that S1 is equal to S2. So in this case, so you can see here the value of this the entropy, the value of entropy. So at these two conditions here, so this is at gaseous condition and this one is at superheated conditions. Okay, so the value of this entropy is given to you. So that means you can see here, so this S1 is equal to S2. So here S1, so is less than the condition which is given at the 2. Okay, which is less. That means the steam is in the wet state. So you have to find the value of X, which is at X at the second condition. Okay, so since S1 is equal to S2, so S1 is equal to, so for S2 you can write as SF2 plus X2 into SG2 minus SF2. So whether you should look at the data that are given to you, whether SF2 is given, SG2 and SF2, that is X2 you have to find out. Okay, so you know the value of S1. So substitute in this formula, you can see here SF2 plus X2 into SG2 minus SF2. So you can see here, so here you can see that SG2 is given to you as well as SF2 is also given to you. So you can see here SG2 and SF2 is given here. So you know the value of S1. So you can easily find the value of X2. So if you find the value of X2, you can find the value of H2. So since it is at a wet condition, H2 will be equal to HF2 plus X2 into HG2 minus HF2. So all these data are known to us. So simply you can substitute there and you can find the value of H2. So from this H2 you can find the value of the work output. So that is given for this that you have to determine in this problem. So the next problem. So a power plant, this is an objective type question and the previous one is a numerical type. So a power plant operating on a simple Rankine cycle as a boiler pressure is given to you. It is 32 bar and the condenser pressure is 0.7 by 5 bar. So the exit state from the steam turbine is dry saturated vapor and the given conditions are here. So this pressure is superheated. You can see here it is a superheated conditions. So this is superheated condition. So and for 592 degrees centigrade the superheated temperature and H value is given 3663 and S value is given. So you have to find the mean temperature of heat supply. Mean temperature, the temperature will be in Kelvin. Okay, so based on this, how can you find the mean temperature? So mean temperature is equal to, it should be in Kelvin. That means if you divide enthalpy and entropy, you can see here enthalpy is kilojoule per kilogram Kelvin, sorry, kilojoule per kilogram, and entropy is kilojoule per kilogram Kelvin. So you can see here this get cancelled, so 1 by k it becomes k. So that means, so there should be enthalpy change. If you consider enthalpy change and the entropy change, so you can get the value of mean temperature of the heat supply. Okay, so you can see how you have to work out this. So now you know that, so that it is the ratio between the enthalpy change and entropy change. So you see here, so this is the diagram which represents this Rankine cycle. So H1 is given to you. We know that S1 is equal to S2, S1 is equal to S2. So the expansion is isentropic and it starts in a superheated state, because the condition that is given to you is superheated condition for superheated steam condition. You can see here superheat steam properties at 32 bar. So it starts at the 32 bar. So it starts at superheated conditions. Okay, pressure. So H1 is given. H1 is 3663. S1 is given. So S1 is equal to S2. S1 is equal to S2. So now the mean temperature of the heat supply, as I told you, so it should be change in enthalpy and change in entropy. So the change in enthalpy, that is from 1 to 4. So H1 minus H4 divided by S1 minus S4 will give you the mean temperature of the heat supply. So you can see here H1 is given to you, H1 is known to us, and then S1 is known, and then S4, you look at the problem that is given to you. So this represents, so S4, so S4 is also given to you, it is 1.2129. Okay, so that is the condition, that is for 2 to 3, it is 0.75, represents 2 to 2 or 3 conditions, and this superheated, when you look at the diagram, you can see that it represents 1 or 4, it represents 1 or 4. So you can see that S3 is also given to you, so that is equal to, S3 is equal to here, when you look at the diagram, S3 is equal to S4, and then S1 is equal to S2. Okay, so S4 is also given to you. So now you are in need of, so H4, so you know the value of H1, everything. So the only unknown is H4. So H4, how can you find the H4, value of H4? So you have to look at the given data. So when you look at the given data, so you can see that the pressure is given to you, condenser pressure, you can see boiler pressure and condenser pressure. So you have to relate this. So when you relate this, so you can see that H4 minus H3 into specific wise will be equal to H4 minus H3 will be equal to this Vf into this pressure of the boiler and pressure of the condenser. So when the difference between the pressure of the boiler and the condenser into Vf, it will give you the value that is H4 minus H3. So H4 minus H3, you know the value of H3 which is given to you. Vf is also given, pressure of the boiler and the pressure of the condenser is given. So you can easily find the value of H4. So substitute the value of H4 here and you can get the value of this. The mean temperature of the heat supply is around 525. You can see here it is around 525 Kelvin. So this is the answer. So for this, so everything it relates with the TS diagram, and you should know the working function. So when it is superheated and when it is condensed. So that means we have studied that it is alternately it is condensed and then it is heated further. So you should know about this diagram thoroughly. Okay, so one is this 1 to 2, 2 to 3, 3 to 4. So here you have S1 is equal to S2 and S3 is equal to S4. The diagram is similar in all the cases. Mostly in Rankine cycle, the diagram is similar, but this may change. It depends upon the condition that is given in the problem. The numbers may change, 1, 2, 3, 4. The numbers may change, it depends upon the condition. Okay. The next one is in the Rankine cycle, when superheated steam is used, so what happens? So when superheated steam is used, surely the thermal efficiency will increase. and the mean temperature of the heat addition or the heat rejection will also increase. Mean temperature will also increase. And then the dryness fraction. So dryness fraction of the steam at the exit of the turbine will also increase. Only when it increases, so it can improve the life of the blades of the turbine. So all the three, that is all the three statements which is given in this Rankine cycle are true. So you have to tick the option D. That is all the options which is given in A, B and C are right. So the option is D. Okay, so you can see here thermal efficiency increases as the mean temperature of heat addition increases. So due to superheating, the dryness fraction of steam at the exit of the turbine also increases. So this is a similar problem. So as that of the previous one, the same problem. So here, so the question is you have to find the value of enthalpy of the steam. Okay, the same problem, but here when you go to the, so in this case you determine the value of work output. So but here you are going to find only the value of the enthalpy at the exit condition, that is at the exit of the turbine. The same problem which is given here. So now we can see about this reheating of steam. So in the case of this reheat cycle, so the expansion of the steam from the initial state 1 to the condenser pressure is carried out in 2 or more steps, so which depends upon the number of reheaters that are used. Okay, so the cycle efficiency here, it improves with the reheat. So you can see that these are the sentences which you have to remember for this reheating of steam. So the sentence that is bold with the sentences which are bold, so are these sentences you have to remember for this reheating of steam. Now the points you have to remember for this. Okay, the cycle efficiency here, it improves with the reheat. So when you use a reheater, the cycle efficiency will improve. However, the cycle efficiency in a single reheat is influenced by pressure at which the steam is reheated. So when you go for a single reheat, it is influenced by the pressure. So the efficiency increases as the reheat pressure is lowered and reaches a peak at a pressure ratio between 0.2 to 0.25. So you have to remember all these points for this reheating of steam. So you can see here, so this is the diagram which represents the reheating cycle. So this one, so 1 to 2, so already you have seen like this. So 1 to, so that is 1 to 2, so 1, so it comes down. So, but in earlier stages, so the line will go straightly towards, that means the entropy remains constant here, S is constant, that is S1 will be equal to that S2. But now when you go for reheat, so it carries once again, so that what is that, it comes down and the temperature increases further and reaches the initial condition, and then it is expanded, so in the turbine. Okay, so for reheat cycle, so this is the diagram which represents the reheating process. So you have to be thorough with this. So that means it reaches to a certain point and once again it reaches the initial condition, and then you are expanding the steam at a isentropic process. So reheating steam also increases the net work output of the turbine. So you can see that so the net work output of the turbine is increased. So from 1 to 4, you can see that the net work output increases. So there are some key points which are for this cycle. So that is, so internally, so irreversibility of this Rankine cycle is caused by fluid frictions, that is throttling and mixing. So you have to remember this. So this will come in statements. Okay, so externally, irreversibility of the Rankine cycle is caused due to the temperature difference between the combustion gases and the working fluid on the same side, and the temperature difference between the condensing working fluid and the condenser cooling water on the sink side. Okay, so you can see here. So these are the statements which are related to this cycle. So what are the advantages, reheat cycle? What are the advantages of reheating? So the net work done increases, heat supply increases, thermal efficiency increases, and due to reheating, the turbine exit dryness fraction increases. The exit dryness fraction increases, so which will prevent the blade erosion, so that the life of the turbine will be increased. Okay, so these are some of the key points related to this reheating. Okay, so then you can see a question for a Rankine cycle with reheating. So far we have seen, so what will happen in a Rankine cycle? So for a Rankine cycle with reheating, which of the following statements are correct? So thermal efficiency will increase. Okay, right. So either it may, thermal efficiency may increase, or otherwise sometimes it may decrease. Okay, so the average temperature of the heat addition will increase, right? Average temperature when steam at the turbine exit becomes drier, right? So here, so you have to add one more point, that is thermal efficiency will either it will increase or decrease. So the answer for this one is only 2 and 3 are correct. You can see here, so that is the features of the Rankine cycle. So what are the features of the Rankine cycle? So you can see here, increase in average temperature of heat addition, thermal efficiency, the thermal efficiency may increase or decrease. The thermal efficiency may, that I have told you earlier, that the thermal efficiency increase, so in some cases it may decrease. So this is a point. So you have to be you have to study it carefully, so that the thermal efficiency may increase is also right. It seems to be right, but it also decrease. So the dry steam at a turbine exit, so that is moisture content of the steam at low pressure turbine exit is decreased. So due to this, blade erosion is reduced. So next one. So if a reheater is added to a Rankine cycle, what will happen? So the network will increase. Sure, the network will increase. So you can see network remains same. That is wrong. The network and efficiency decrease is wrong. Network increase. Right. So you have two options, one is A and D, but what happens to the other you can see, but the efficiency may increase or decrease. But here it is, the efficiency remains same. So you may not able to select this answer. So the correct answer is the network increases, but the efficiency may increase or decrease. The option is A. That you can see here. So what I have given to you. So reheat Rankine cycle is employed when high pressure turbine are used, and the dryness fraction at outlet of the turbine will reduce below the acceptable limit 88%. Okay, to avoid this condition, the steam is partially expanded in high pressure turbine and then reheated to the same initial temperature. Further, it is expanded in low pressure turbine, which increases the net work output. So the net work output increases, but increase the dryness fraction. The efficiency here, it may increase or decrease. Okay, so this is a statement which we have given earlier as a right answer. You can see the net work increases, but the efficiency may increase or decrease. Okay, so now, so you can see a problem, that is a numerical problem with an objective type problem, so which has a reheat cycle. So find the efficiency of the reheat cycle as shown below. So pump work is given to you and steam flow rate is given. Find the efficiency. So the efficiency, so what is the efficiency of this cycle? So when you look at this diagram, you can see that you have a high pressure turbine, low pressure turbine, then a condenser is there, pump is there, and boiler is there. Okay, so the pump work is given to you. So it is 20 kilojoule per kilogram. That is the pump work. Okay, so if you add H5 with this pump work, you will get the value of H6. Am I right? If you add these two, you will get 320. I think 300 plus 20, 320 will be the value of H6. Right. So now, so you know that it is output by input, efficiency of the cycle. What is the output? So output is work done by the turbine. Work done by the turbine. So you can see that, and input is the amount of heat energy that is supplied. amount of heat energy that is supplied. So what is the work that is done by the turbine here? So H1, so you can see here H1 minus H2 plus H3 minus H4 will be the work that is carried out by the turbine. Alright, so H1 minus H2 plus H3 minus H4 will be the net work carried out by the turbine. So all the data are known to you. H1, H2, H3 and H4 are known to you. Then H6 I told you 300 plus 20 will give you 320 kilojoule per kilogram. And now we should know, we are in need of the amount of heat energy that is supplied. So what is the amount of heat energy that is supplied? That is H1 minus H6. H1 minus H6, so it is the plus this energy, that is H3 minus H4, am I right? Not H4, that is so you have to subtract these two energies, not H4, it is H3 minus H2. So when you subtract this H3 and H2 and add with H1 difference H6, so you will get the total amount of heat energy that is to be supplied. You can see here. So the network is H1 minus H2 plus H3 minus H4. So you got the value of H6. Okay, then heat supplied is H1 minus H6, then H3 minus H2. If you add these two, you will get the value of this heat that is supplied. So the net work output is known to us. It is 1240 and this is 3350. Okay, so you will get the value of efficiency. It is 37%. Okay, the answer is C, it is 37%. The next question. So in a steam power plant, steam is first expanded isentropically in a turbine from an initial condition of 100 bar and 500 degrees centigrade to a pressure of 40 bar. Then the steam is reheated up to 500 degrees centigrade at a constant pressure. So the steam, so you can see that, so in a steam power plant, steam is first expanded isentropically in a turbine. So steam is expanded isentropically in a turbine. So you draw that TS diagram. It is expanded isentropically. So from out of the condition it is 100 bar and 500 degrees centigrade. So 500 degrees centigrade and 100 bar to a pressure of 40 bar. So it reaches 40 bar. This is a TS diagram, 40 bar. Then the steam is reheated. Now only we have seen that reheated cycle. Steam is reheated up to once again the same 500 degrees centigrade at a constant pressure. So this is constant pressure process. At a constant pressure, the steam is 10, then it is expanded isentropically to another turbine up to a condenser pressure of 0.01 bar. So this is 0.01 bar. So you will get a curve like this. Okay. So you can see in this diagram, so that is the curve is like this. So the curve is like this. So it does not touch this line, the dry saturated line. So the curve is like this. So what is the question? So the question is the dryness fraction at the condenser inlet. So you have to find the dryness fraction at the condenser inlet, that is S. Dryness fraction is X4. So X4 at the part 0.4. So this is the condenser inlet, right? So a lot of data are given to you. So the only hint is S3 is equal to S4. Right, so you know the value of S3, right? It is given to you or not? So you look at the diagram, data that are given to you. S3 is 7.0901. So S3 is given to you. So that is equal to S4. So which is equal to that is equal to S3 is equal to S4, that is equal to SF4 plus X4 into SG4 minus SF4. So this is the equation. So from this you can easily find, you know, this value, and SF4 is 0.1059 and SG4 is 8.9756. So all these values are known to you. So the only unknown is X4. So simply you can use. So the other data that are given, so you can see some other data, superfluous data are given to you. So in order to confuse you, so write 0.1059 plus X into 8.9756 minus 0.1059. So you get the value as 0.79. Okay. So this is about reheating. So you in reheating you can see how the problem comes. So you will get statements. So that is with the true, whether it is which one is right or which of the following statements are true or false, and you will get the problems which are related to this TS diagram. Okay. So then regeneration, the mean temperature of heat addition can also be increased by reducing the amount of heat added at low temperatures, especially in the economizer section of the steam generator. So in the regeneration process, energy is exchanged internally between the expanding fluid in the turbine and the compressed fluid before this heat addition takes place. So you can see here, so this is a ideal regenerative cycle. So this ideal regeneration, it do not affect the work output from the turbine. It is more efficient with a high steam rate. So you can see here, so you have n number of process, you can see 1 to 2, 2 to 3 and 4. So you can see that regeneration, so how the regeneration takes place. So in all these cases, so for first one it is 1 minus 1. Suppose if 1 kilogram of this fluid is supplied, it is 1 minus M1, and for the second it is 1 minus M1 minus M2. Okay, the same will be supplied to this point. Okay. So what are the advantages of regeneration cycle? Heat supplied to the boiler become reduced. So the heat supplied is reduced and thermal efficiency is increased, and since the average temperature of the heat addition to the cycle is increased. So why the thermal efficiency is increased? The average temperature of heat addition to the cycle is increased. That is why the thermal efficiency increases. And due to bleeding in the turbine, so erosion of the turbine due to this moisture is reduced. Okay, so we are making exit conditions of the turbine as drier, so that we can the erosion of the turbine blades is reduced due to the moisture, because the moisture content is reduced there. So that is the advantages of this regeneration. So now we can see the problems which are related to this regeneration process. So you can see here, so that say a problem is given to you. A steam power cycle with a single stage regeneration is here. It is shown. So an open feed water, that is OFWH, open feed water heater, is used for regeneration purpose. So the enthalpy at each and every point is given to you at state 1 and state 2, then 3, 4, 5 is given to you. If the bleed from the turbine at the state 2 is 30%, what will be the enthalpy of the steam after exiting from this regenerator? So from this regenerator, so what will be the, so from the regenerator, so what will be the exit? But you can see here the bleed from the turbine at state 2 is only 30%. So if you think that the 1 kg of steam is generated in the boiler, the bleed from the turbine at state 2 will be 30% of 1 kg will be equal to 0.3 kilogram. So this is the diagram which represents the problem. So you can see that, so if x kg, that is x kg is supplied, so you can see that so H2 for the enthalpy of enthalpy at this point is H2, and from 2 so to the OF, that is open feed water heater, so x kg of this fluid is supplied, and similarly if it is x kg, this becomes 1 minus x kg, and for at the sixth at point 6, at condition 6, it is So you can see that it is 1 kg. So by energy balance, so this H5 into 1 minus x plus x into H2, that is H5 into 1 minus x plus H2 into x minus H6 into 1 is equal to 0. So you can see here, so that is, so this will be equal to H6 into 1, right? So the unknown, so you know the value of H5, then H2, the value of this x, the value of x is 0.3 kilogram. So x is known to you, so you can easily find the value of the unknown H6. The value of H6 is 1114 kilojoule per kilogram, is nothing but the enthalpy of stream at the exit condition. So at this exit condition where this regenerator is used, so that is 6, that is 6th position. So you can find the value of the enthalpy of this stream at the exit. So the next one is an ideal regenerative Rankine cycle. It employs one open feed water heater which operates at 1.2 megapascal. So the extracted steam, it leaves the turbine at 220 degrees centigrade. The condensate enters the feed water heater at an enthalpy of 195 Kelvin. The condensate enters this feed water heater. So this is the feed water heater. It enters at 195 kilojoule per kilogram. Okay. So then water property is given, that is 2862 kilojoule at 1.2 megapascal and 220 degrees centigrade. So 28 H1, that is the value of H1 is given, that is 2862, and we don't know the mass. So if this is m, so this will be 1 minus m. Okay. And the saturated liquid at 1.2 megapascal is equal to 800 kilojoule per kilogram. That is the value of H3 is given, it is 800 kilojoule, right? Okay, so now you have to make an equation, a balanced equation. So the sum of these two will be equal to H3. So m into H1 plus 1 minus m into H2 will be equal to H3. So you simplify this equation, so bring H2 to one side, so that is m to one side, m into H1 minus H2 will be equal to H3 minus H2. So m you can get, so you know all the values, so you can, the mass flow fraction will be given, that is 0.227. So what is the answer? It is B, it is 0.227. Okay, so the mass flow fraction is, so you should know how to balance the equation according to the data that are given to you. Okay. So the next one is the efficiency of the steam power plant. So overall efficiency is the product of boiler efficiency, cycle efficiency, turbine efficiency, generator efficiency and auxiliary efficiency. So these are the definitions for this boiler efficiency, turbine efficiency. So if it is the ratio between rate of energy absorption by water from steam and rate of energy released by combustion of fuel. And for the mechanical efficiency of the turbine, brake output and between ratio between brake output and internal output. And when it is auxiliary efficiency, the net power transmitted by the generator and the gross power produced by the plant. And cycle, it is cycle efficiency, it is network output and heat supplied. And the efficiency of the generator, electrical output at generator terminal and the brake output of the turbine. So these are the points you have to remember in this, that is reheating of the steam, it improved the thermal efficiency of the plant, the net work output of the turbine, reduction in blade erosion. So by using this regeneration, the thermal efficiency of the plant can be increased, but it does not affect the work output from the turbine. So these are the statements you have to remember which are related to this reheating as well as regeneration. So next is combined cycle power generation. So it is an assembly of heat engines that work with the same source of heat. So the principle of this combined power generation is, so the exhaust of one heat engine is used as the source for the other. So this process increases the overall efficiency of a heat engine. So it increases the overall efficiency of a heat engine. Okay. So what are the characteristics? So it should have, the fluid should have high critical temperature. That is the characteristics of a ideal working fluid. So the specific heat of the liquid should be small. So and then it should be the very close. So that is the saturated vapor line. So the saturated vapor line. So this is the saturated vapor line. So this saturated vapor line of a TS diagram, so should be very close to the turbine expansion process. Suppose, so when this at superheat condition when it is expanded like this at a constant isentropic process, so this should end at either near to this dry saturated line or at the dry saturated line or nearer to the dry saturated line. Okay, right. So the freezing point of the fluid should be below this room temperature. So the fluid should be chemically stable, non-toxic, non-corrosive and not excessively viscous, and it should be low in cost. So a question is there, efficiency of the Rankine cycle can be increased by, how can you increase the efficiency of the Rankine cycle? The options are given. So increasing the condenser pressure, decreasing the condenser pressure, decreasing boiler pressure, and none of this. So we know that, so now we have studied now. So it is related with the condenser pressure. So when you decrease the condenser pressure, so you can improve the efficiency of the cycle. You can see here, by decreasing the condenser pressure, the mean temperature of heat addition as well as heat rejection, it decreases. So when it further decreases, the gap between this mean temperature of heat addition and the mean temperature of the heat rejection, it increases. So it is in the denominator side. So the numerator side it will be same, but anyhow the efficiency will increase. Okay, the next question. So is a simple Rankine cycle works between the pressure limits of 28 bar and 0.06 bar, the initial condition of the steam being dry. So what is the work ratio? So work ratio is the net work and the turbine work. Okay, it is the ratio between these two, you can see here. So the net work and the turbine work. So what is the net work? So net work is nothing but the difference between the work done by the turbine and the work done by the pump. So work done by the turbine should be known to you. So what is the work done by the turbine? What is the work done by the turbine? It is the difference between H2 and H3, you can see. So in this problem you can see that, so these two represents the turbine area. So because it has a higher enthalpy, so H2 minus H3 will give you the value of this turbine work. So H2 minus H3, so that is 3000 minus 2000 is 1000, and then pump work is H1 minus H4, so that is 150 minus 145, so you will get 1000 minus 5 divided by 1000, you will get a 0.995. So that is the answer for this one. Okay. Is 0.995. So the next one, the overall efficiency of the thermal power plant is, what is the overall efficiency? So yes, the boiler efficiency is there, turbine efficiency, generator efficiency, you can see in all this. So you don't have this gas cycle efficiency, here you have only, so these are all not the options. So the only option is B, so the answer B is right. Okay. Next one is, in a steam power plant, two cycles are coupled in series, where the first cycle has an efficiency of 30% and the second cycle has an efficiency of how much it is, 20%. Determine the combined overall cycle efficiency. So you can see here the formula, 1 minus eta is equal to, that is 1 minus eta will be equal to 1 minus eta 1 and 1 minus eta 2, and it goes on up to 1 minus eta n. Okay, so this can be written as that overall combined efficiency can be written as eta. So eta, which is equal to, when you simplify this, will be equal to eta 1 plus eta 2, then minus eta 1 into eta 2. So you know all the values, substitute and find the multiply by 100. So you will get the value in terms of percentage. Okay, next one is employing superheated steam in turbines, it leads to. So when you employ a superheated steam in blades turbine, so you can see that, so what will happen? So decrease in, so you can see that superheated steam in turbines leads to decrease of this erosion of turbine blades. So the option is B. Okay, so directly you can answer for these things because we know all this. What is the specific steam consumption in kilogram per kilowatt hour of the Rankine cycle based on net output if the enthalpies at turbine inlet enthalpy is given to you and the exit enthalpy is given. What is the specific work? That is specific work by the pump is also given to you. So you have to find the value of specific steam consumption. So for per kilowatt hour. Okay, so 1 kilowatt hour, you know how many joules it is? For 1 kilowatt hour, it is 3600 kilojoule. So for this 3000, how much of this specific steam consumption has to be determined based on the net output if the enthalpies are at a turbine inlet and turbine exit are given to you. So you can see that the specific steam consumption is, so for 3600, okay, so 3600 kilojoule per kilojoule. So the turbine, you should know the work done by the turbine. So the net work done by the turbine is H1 minus H2, it is given there. So what is the net work? That is 3200 minus 2050, that is given there, and the net work is WT minus WP. So pump work is given, yes, pump work, yes, it is given there, it is 1.5 kilojoule per kilogram. So the 1150 minus 1.5, you will get this. So if you divide that value 1148.5, so you will get the value of the specific heat consumption. So you should know if it is for kilowatt hour, so then you have to find for this in terms of this what is that kilojoule, that is 3600 kilojoule. 1 kilowatt hour should be equal to or is equal to 3600 kilojoule. It should be known to you. Okay, the next one is consider a simple Rankine cycle with fixed turbine inlet conditions. So what is the effect of lowering the condenser pressure? So what is the effect of lowering the condenser pressure? So we have seen, now only we have seen, so in condenser pressure, what happens? So when you decrease the condenser pressure further the heat addition increases and heat rejection also, the gap between those two increases, and at last it increases the cycle efficiency. So the cycle efficiency increase is the correct answer for this one. So because when you lower the condenser pressure, so you can see the efficiency, the cycle efficiency is increased. Next one, a condenser in a steam power plant. So what happens to the condenser in steam power plant? You can see that it increases the expansion ratio of steam, it reduces the back pressure of the steam, it reduces the temperature of the exhaust steam. Sure, the condenser, so because it is used for condensing that exhaust which is coming out from the turbine, so it reduces the temperature and also it reduces the back pressure of the steam and also it increases the expansion ratio, because the main function of the turbine before this condenser is expansion. So thereby, so the condenser, when you keep the condenser after this turbine, it increases the expansion ratio of the steam. So all the three answers are right. So the option is all of the above. So D is the right answer for this. And the next one is, in Rankine cycle, expansion of steam is assumed to be. So we all know that obviously the answer is isentropic. Okay, the answer is isentropic. Okay, it is isentropic. So increasing boiler pressure causes, so which of the following in Rankine cycle? So what will happen when you increase the boiler pressure? So decrease the condenser pressure we have seen. So now increasing the boiler pressure, what happens in this Rankine cycle? Surely it will increase the pump work. So pump work will increase, and efficiency, you can see that here. So turbine work increases, pump work increases. Okay, so the dryness fraction of the steam at turbine exhaust decreases. That is not given here. All these options are not given. So the only thing is turbine work is not given here. So increase in pump work. So the option will be A for this. So the option will be A, will be the best answer for this question. So you can see this diagram. So when you increase that boiler pressure, what happens? Okay. The next question. So following data is obtained from a Rankine power plant. Enthalpy at turbine inlet is given to you, and after expansion is given to you. Heat addition is also there. So pump work is also there. Generator efficiency is given. So you have to calculate the overall plant efficiency for the given percentage. That is for 95%. So that means for 0.95. So what is the value of this plant efficiency? So you have to find the plant efficiency and multiply it by 0.95. So you know the efficiency is work done. What is the work done? WT minus WP divided by heat energy that is supplied. The heat energy supplied is given here. It is 2700 kilojoule. So WT, so 2765 minus, so 1560. Then WP is 20 minus 20. So divided by, am I right? This is 1205 minus 20. So divided by this 2700. So this will give you the efficiency. So but you have to find the efficiency for 95%. So into 0.95. So you will get the answer, that is 41.69%. So next one. In Rankine cycle, so lower limit on the condenser pressure is due to. So lower limit on the condenser pressure is due to, so what is the answer? Saturation temperature at that pressure, freezing temperature at that atmospheric pressure, expansion limit in the turbine, so lower critical temperature, these are all wrong. Freezing temperature at the atmosphere, oh no. So the saturation temperature at that pressure will be the exact answer. So for this question. Okay, the next one. For two cycles coupled in series, so topping cycle has an efficiency 40% and the bottoming cycle has an efficiency of 30%. The overall combined cycle efficiency. So now only we have seen a equation, that is 1 minus eta is equal to 1 minus eta 1 into 1 minus eta 2, and it goes up to 1 minus eta n. So that is eta is given as eta 1 plus eta 2 minus eta 1 into eta 2. So use that formula to find this, that is 0.4 plus 0.3 minus 0.4 into 0.3. So am I right? Yes, 0.4 into 0. So the answer is 58%. So you will get the value of as 58%, and the option is C for this. Okay, right. The next question, a steam power plant working on Rankine cycle have saturated vapor at the exit of the turbine. Steam enters the turbine at 20 bar, that is 350 degrees centigrade. Hg is given. The enthalpy at this point is steam enters the turbine is given to you and leaves the turbine. Enthalpy is given, Hf is given, and the Hfg is given to you. So you have to find the value of Hg for this exit. So that is Hg2. Am I right? Hg2 should be equal to, that is Hfg is equal to Hg minus Hf. So if you add these two, you will get, I think you will get the value of Hg2. Right? Right. So if you add these two, you will get the value of Hg2. So the turbine work is the same. Turbine work is H1 minus H2. So you will get the answer, and the amount of heat energy that is supplied is H1 minus H4. So you know this, H1 minus H4. So that is the efficiency. Eta is equal to the output work by the amount of heat energy that is supplied. So that is this output or work output, whatever may be. So you know all these values, so substitute, you will get the answer as 20.64. Okay, so with this, so you can see that, so we have seen a lot of problems in Rankine cycle related to the simple Rankine cycle, so without reheating and regeneration, and also the Rankine cycle with regeneration and reheating, and the overall this combined cycle power plants. So students should be thorough with the working function of the Rankine cycle, because so in each and every question, gate question, you are getting problems which are related to this Rankine cycle with either with regeneration or reheating. So be thorough with these concepts on this regeneration and reheating with Rankine cycle. So please you work out those problems, n number of problems, so that you 3 to 4 marks. So you will surely you can get 3 to 4 marks in that gate. So when you study this Rankine cycle. So thank you.